Let's take a look at the CSTR equipment that we have in the unit operations lab. The apparatus is as follows. We have a glass reactor vessel, which contains our liquid reactants where reaction occurs. And in this, we have two pumps that we can control the feed rate of our two reactants. We have a sodium hydroxide stock tank, and its pump will deliver that flow into the reactor. And we also have a stock tank of ethyl acetate, and its pump will deliver it to the reactor. The flow rates are controlled by a control valve situated on individual rotometers. And these rotometers are, the purpose is to read the flow rate of the reactant into the vessel. There's a recirculation line on these pumps so that excess liquid coming out of the pump gets returned to the stock tank for both the sodium hydroxide and the ethyl acetate. So you would create a mixture of sodium hydroxide and water for the sodium hydroxide stock tank and an ethyl acetate and water in the ethyl acetate stock tank. The vessel operates where the flow rate of our reactants comes in through the bottom, and the liquid leaves by what we call an overflow tube, and this is used to control the liquid height at a position that we desire, and that flow rate will come out of the reactor and into the drain. The solution is mixed using a variable speed mixer. You would control its speed by the voltage that you would supply to the mixer motor. And we will monitor the reaction progress using a conductivity probe, and the signal from that probe goes to our data acquisition system. The volume we control by the height of this overflow tube, and it's currently set, and you would need to be able to measure what the volume of liquid is in that reactor so you can know what the reactor volume is during the course of the experiment. And in this simulation, we're going to initially just put in pure water into our vessel, and we can do that by lifting the lid off of the reactor vessel and pouring in water from a graduated cylinder, and note how much water we actually poured in when that liquid first reaches the overflow tube. The lid would then be positioned back onto the reactor during the course of the study. Now let's take a look at what we're going to measure. We're going to control the volumetric flow rate of the sodium hydroxide solution and the ethyl acetate solution into the reactor. And during the course of time, we're going to monitor the conductivity measurement. Let's look at the overall governing material balance equations. We have ionic species of sodium hydroxide in water. It's going to react with the ethyl acetate that's in water to form ethanol and sodium acetate. Note that the sodium is in ionic form on both sides of the equation, so the sodium concentration as an ion will not change during the course of the reaction. Hydroxide ion, however, will change during the course of the reaction because it's going to combine with the ethyl acetate to form ethanol, and that will also liberate the acetate ion into solution. Now, the only contributors to the conductivity of our solution mixture are the ionic species, sodium, hydroxide, and acetate ion, plus whatever conductivity we may have in our water that wasn't purified out during the demineralization. Our reaction rate is a value of a rate constant K. We're going to have a hydroxide ion concentration raised to the alpha power, and the ethyl acetate concentration raised to the beta power. And we are to determine these three values using the batch reaction that we've done previously. Now let's look at our governing equation. Accumulation of any species in this reactor vessel will equal the input by flow minus the output by flow, plus generation minus consumption via chemical reaction. We can look at each of the species separately. The accumulation term is just a derivative of, in this case, our sodium ion concentration with respect to time, and multiply that by the reactor volume, which we have to measure. And that will equal the volumetric flow rate times the concentration of sodium hydroxide coming in through the pump, minus what's leaving, and that volumetric flow rate coming out multiplied by the sodium ion concentration in the solution. If this system is well mixed, the concentration of sodium ion leaving will equal that of in the vessel itself. As stated before, the sodium ion does not get depleted or generated via reaction in this case. We would do the same for the hydroxide ion. Its accumulation term will equal what's coming in by flow minus what's leaving the reactor by flow. And the reaction is going to consume hydroxide ion by this equation, and that will be equal to the rate of reaction times the volume of the reactor V. Ethyl acetate in a similar fashion, what comes in by flow, this case in stream 2, minus what's leaving, minus what's consumed by reaction given by the reaction rate times the reactor volume V. The acetate ion, its accumulation will be what's leaving the reactor. There is no acetate coming in, so it has no input, plus what's created via reaction, which is the rate of reaction times the volume. And we can then do a simple balance that at hydraulic steady state, when the level doesn't change with time, the volumetric flow rate of the inputs will equal the volumetric flow rate of output. So V3 will equal V dot 1 and V dot 2. Those two added together. And to help us work with the differential equation, we're going to do an approximation where the change of concentration of species I with respect to time, that derivative will approximate as a change in concentration from one time to the next divided by the time interval. And if we keep our delta t small, this is a fairly accurate representation of the derivative since things do not change appreciably with time. Therefore, we can calculate the concentration at the next time step will be equal to the concentration at the previous time step plus the derivative evaluated at the previous time step times delta t. The conductivity of this solution will equal the conductivity of water plus the concentration of sodium ion times its molar conductivity plus the concentration of hydroxide ion times its molar conductivity plus the concentration of acetate times its molar conductivity. One thing we should know is that the flow meters that we have used in this experiment need to be calibrated. And this is done by an experiment where we set our pump flow rates going through the flow meter at the settings on the rotometer, and we actually measured the flow rate that passes through the flow meter, and do that for the pump A and the pump B. And we notice that there's an appreciable difference between the reading on the rotometer and the actual flow. And we can see this on this plot. For the sodium hydroxide pump, we see that the flow rate, the flow meter reading, although it is fairly linear, uh, there is a significant difference between the actual flow and the reading on that flow meter. Did the same thing for our uh, ethyl acetate pump, and we find that its flow rate is slightly higher than what we see on the rotometer. And so we would need to come up with a calibration curve. We can do a linear fit, and this was done for both pump A and pump B. And for pump A, the slope was equal to 0.73 and the intercept at 7.5. And for the pump B, 1.11 and the intercept at 0.649. Meaning that if we're reading 100 on pump A, we're actually going to calculate the true flow rate being approximately 94 mils per minute. So in your calculations, you'll record these values off the rotometer, but you're going to have to calculate what the true flow rates are. And this will allow you to do more accurate calculations when you calibrate the flow meters. Now let's take a look at our calculations. A couple of variables we want to include in the calculations. One is the measured reactor volume that you'll have to measure when you put in the initial water solution. In this case, we'll say it's 1.8 liters. And the conductivity of that water in that vessel is 400 microsiemens per centimeter. Our stock tank, we're going to measure out 50% sodium hydroxide and ethyl acetate and put it into our stock tank, where each tank will contain 20 liters of water initially. So let's say we put in 70 grams of that 50% solution in the sodium hydroxide stock tank and 170 grams of ethyl acetate in its stock tank. The concentration of sodium hydroxide in that tank can be calculated, where it will be equal to the mass of sodium hydroxide. Its concentration is 50%, so we would have to multiply it by 0.5. We would divide it by its molecular weight, which is 40, and divide it by the volume in that particular tank. Likewise, for our ethyl acetate, we measured out 170 grams. Its molecular weight is 88.1 grams per gram mole, and the volume, it's also 20 liters. So our concentrations coming in are calculated. We're going to need our rate constant K, the value of alpha and beta that we determined from the batch experiment. So for this exercise, we'll say K is 1.89, the OH coefficient alpha is 0.83, and the ethyl acetate coefficient beta is 1.02. In the course of the experiment, we're going to run different flow rates of the hydroxide and ethyl acetate into the reactor. So we're going to look at different combinations of volumetric flow rates going into the reactor for each one. So looking at 200 milliliters per minute of sodium hydroxide flow at time 0, and we'll use a value of 210 milliliters per minute of ethyl acetate at time 0. These are the actual flow rate readings. Remember that the rotometer readings will have to be compensated for the actual flows for this exercise. At 30 minutes, we'll switch the flow rate from 200 to 150 for sodium hydroxide, 210 to 160 for the ethyl acetate, And at 60 minutes, we're going to change the flow rate down to 50 for sodium hydroxide and 60 for ethyl acetate. Our flow rates leaving the reactor are just the sum of these two flow rates coming in. And we also want to look at the residence time. Now, the residence time is equal to the volume of the reactor divided by the volumetric flow rate going through the reactor. And we have 1.8 liters for the volume of the reactor. And in the first initial part of the experiment, we have 410 milliliters per minute. So we would calculate what the residence time is by taking the volume of the reactor. We'll multiply it by 1,000 to get it into milliliters, and then divide it by the total flow going through the reactor. And we're going to multiply it by a value of 5. And the reason why 5 is chosen is because with the CSTR, if you go through 5 residence times in the reactor, you're pretty much guaranteed that you're quite near steady state. And so we want to make sure enough time has elapsed before we make a change to make sure that we reach steady state. So at this flow rate, we would expect steady state to occur at 22 minutes. So we don't want to make any changes in the flow rates until a minimum of 22 minutes have passed. So I selected 30 minutes for the change in flow rates from 200 and 210 to 150 and 160. So at 310 total flow, the 5 times tau is 29 minutes. So I want to make sure another 30 minutes have elapsed until I make my next change. So at 60 minutes, I'll change my flow rates. And we want to allow a significant amount of time to elapse to reach steady state for that last one. In this case, 82 minutes. We're also going to need to know what our specific ion conductivity is for the various ions. And this is given by the calculated values based on the temperature of your reactor. So in my case, I'm just using values of 50,240, but you would actually calculate it based on the temperature that you measure for your reactor. I'm going to use a time step of 1 minute in my analysis. So I'm going to create a table at time 0. My initial conductivity is just the conductivity of water, which we measure to be at 400 microsiemens per centimeter. We have no sodium hydroxide, ethyl acetate, or sodium acetate in that reactor because we just added water to it. So their concentrations are going to be 0. So when I calculate the conductivity, it's going to be equal to that 400 initial plus the concentration of sodium hydroxide times its ionic conductivity plus that of hydroxide ion and the acetate ion. My volumetric flow rate, V.1 and V.2, changes with time because we're going to use these settings here. And so I need to find a way of calculating what those are when we reach a certain time. I want it to change when we reach 30 minutes to change it to 150. And then at 60 minutes, change to 50. And we can do that using an if statement. The way it works is that volumetric flow rate, if the time, which is F15, is less than 30 minutes, K5, then the flow rate for sodium hydroxide is going to be equal to that first value of V.1 and I'm going to divide it by 1,000 to get it into liters. If it's greater than K dot 5, we're going to have another if statement. If that time is less than K6, which is 60 minutes, then it's going to be equal to the value at the 30-minute time period, in this case 150 divided by 1,000. If the time is greater than 30 or 60 minutes, then that value is going to be equal to the value that we have for that final time step divided by 1,000. And we would have a similar expression for the sodium hydroxide, the ethyl acetate solution. And we can use these if statements to change those values as time goes on. Now we're going to look at calculating our concentrations with time. Here are the equations that we're going to use. Our change in sodium ion concentration with respect to time will be equal to what's coming in by flow, which is the concentration in the stock tank, times the volumetric flow rate of the solution coming with that pump, and divide it by the volume of our reactor, minus what's leaving. In that case, V dot 3 divided by the volume of my reactor times the concentration of sodium ion leaving. Hydroxide, ethyl acetate, and sodium acetate ions are done similarly, except they have the reaction terms. So if I look at my derivative of sodium hydroxide, in this case the sodium ion, we'll find that coming in, I'm going to have my V dot 1. I'm going to divide by my reactor volume and multiply it by the stock concentration of sodium hydroxide. Leaving is V dot 3 divided by my reactor volume and multiply it by the sodium ion concentration in the vessel. Hydroxide ion, again, coming in, I have my volumetric flow rate of stream 1 divided by the reactor volume, which is 3C3, and I'm going to multiply it by the hydroxide ion in that stock tank, which is the same as the sodium ion in that stock tank, minus what's leaving, which is V dot 3 divided by the reactor volume times the concentration of hydroxide ion. And then I'm going to subtract off the reaction rate, which is equal to our rate constant K, in this case H dot 4, multiplied by the hydroxide ion raised to the alpha power times the ethyl acetate ion raised to the beta power. And we would end up with a similar equation for the ethyl acetate, but in this case, what's coming in is the volumetric flow rate of stream 2. And for our acetate ion, it's going to be equal to what's leaving in stream 3 will be a negative because it's an outflow times its ionic concentration plus what's generated by reaction, which is our rate constant, our hydroxide ion raised to the alpha power, and the ethyl acetate raised to the beta power. So I have my derivatives at time 0 for the next step in the calculation. My time step is 1, so my next time is going to be equal to the previous time plus 1. In this case, that's 1 minute. My sodium ion concentration in the vessel is equal to the previous sodium ion concentration plus the derivative times the change in time, which is 1 minus 0, which will equal 1. My hydroxide ion, same calculation. It's going to be equal to the previous value plus the derivative times the difference in time. My ethyl acetate will be equal to the previous ethyl acetate times its derivative times the change in time. And finally, my acetate ion, same expression where we look at the previous value and add to it the derivative times the change in time. So now I can calculate my K using the values of the specific molar conductivities and the concentrations of each species at that time. And I copy down my formulas so that I can come up with how the change in concentration in the CSTR, how that will be as a function of the time in the reactor. Let's take a look at it in a plot. Okay, we have three things plotted on my curve. One is my sodium hydroxide flow rate. The other is the ethyl acetate flow rate. Those are measured on the right-hand y-axis. And the solution conductivity is measured on the left-hand axis. So initially we have 210 milliliters per minute of ethyl acetate and 200 milliliters per minute of sodium hydroxide. So we see our concentration of, or actually conductivity, increase as we start pumping in the flow of hydroxide and ethyl acetate. And then it starts to level off. And then when we slow down our volumetric flow rates, what we're actually doing is giving our solution more residence time to react. And as the solution reacts, we actually consume more of our hydroxide ion, which causes our conductivity to decrease. And then at 60 minutes, we find that the conductivity starts to decay and it starts to come up to a final value. Now let's take a look at these steady states. Notice that it took a good 25 minutes to 30 minutes to achieve a steady state for the initial flow rates. Again, similar 30 minutes for the lower flow rates. And then finally, it takes a longer time to reach a steady state for the small flow rates. And so even at 60 minutes, we're not quite there at steady state, but we can see how changing the flow rates going in will affect the concentration of sodium hydroxide and sodium acetate formation during our CST run. So this is how we would do the modeling work for the dynamic simulation of the CSTR. We would use our model to predict the conductivity, and then we would use the conductivity data that we gathered in the experiment and compare how these two curves line up with each other. If everything was done exactly perfectly, then our conductivity measured values would fall right along this curve here, indicating that we have indeed a good model for our system. I wish you good luck in your analysis, and I hope that this simulation will be useful for you.